Okay, so as you see that if these are the equations, this is the solution that I have, and these are the solutions that we should be concerned about. Rest we can just conclude from here. Now let us follow the drill that we have learned. So solutions are with us. Now we want to know these are what kind of fixed points they are to draw the phase space, right? So take one by one. One by one, we take one of these solutions and see if they are nodes, stable or unstable, centers, or what they are. Okay, just from our Jacobian matrix. So let us write down the Jacobian matrix. Step 4. Jacobian matrix A. Let us calculate it with this set of equations. So these equations are my driving equations for now. I will calculate the Jacobian matrix and I plug in the values of the fixed points one by one to see that they are what kind of fixed points they are. Okay. So Jacobian, tell me what are the values that you are seeing. Please do the calculation.
0, 1 minus cos theta 0.
0, 1. Here.
Minus cos
Minus cos theta.
and 0.
And 0. Got it, everyone? Someone else, please confirm that this is the Jacobian that we have.
Yes, ma'am.
Fine. Okay. So let us find out the value of this Jacobian at 0, 0 first. Okay. So at 0, 0, rest of them are all numbers. So this one becomes -1, right? So the Jacobian at 0, 0, the Jacobian at 0, 0 is given by 0, 1, -1, 0. Okay, so this is the Jacobian that we have. Next, what should we do? What should we do now? Lambdas. Okay, so lambdas of this Jacobian is going to tell me what kind of a fixed point do I have here. So this one is not diagonalized. We can see that off diagonal terms are 1 and -1. Diagonal terms are still 0. So just quickly figure out what the lambda values are for this matrix. So today I will want you to do most of the job and you just confirm that this is the solution that you have. Okay. So what are the lambdas for this matrix? Someone else please say. So
Plus minus iota. Plus minus iota.
Okay. Plus minus I. Everyone got it? Rashmita, got it? Simple, right?
Yeah.
Yeah. So what is the conclusion? If lambda is plus minus I, what kind of fixed point we are looking at? No real part, right?
Ma'am.
Yeah. Yes.
Ma'am, last class you have said that the linearization is not good for center and.
Yeah. I told that. And why so? That is also something that I will discuss today only. Okay.
Like a center, right? No.
This is a center, right? Because we don't have any real part here. And that leads to a center. Okay. So this is a center that we have here. So what are centers? Let us just refresh our memories that what are centers? Centers are basically points around which a system oscillates. So if you have a point on phase space, you can draw numerous trajectories around that particular point. Okay, numerous trajectories which are, we call them neutrally stable. Why neutrally stable? Because if you let them oscillate on that, they will go on doing that forever. If you perturb it a little bit, they will shift to the next trajectory and move away from this one. Okay, so you cannot definitely say this is a stable or an unstable system, because if you let them oscillate in one of them, it will go on oscillating there. If you just push them further a little bit, perturb them a little bit, they end up on another trajectory and repeat the same behavior, but with some different amplitude. Okay, so that is why we call centers neutrally stable. Now let us just try to understand if that is the kind of behavior that we see in our oscillators. If we don't consider any damping into the picture, then the pendulum that we see most of the time behaves like this, right? So this is the solution that we are looking at right now, is the solution that reflects the behavior that we already have seen, that if it is oscillating, it will go on oscillating, right? It will go on oscillating without any damping or anything, because there is no damping in our equation for now. So it will go on oscillating. If you perturb it a little bit, if you increase the amplitude a little bit, it will suddenly shift to a different amplitude and go on oscillating in that bigger amplitude, right? So that behavior that we see in a normal simple harmonic oscillator, that we expect in a normal simple harmonic oscillator, matches with the center behavior. So first thing that we understand is 0, 0 is the center of these dynamics that we have here. Okay, so but we are still left with another solution. So this is the solution that we have here, is somewhat similar to what our previous solutions referred to, but I have a different solution here, and let us see what that means. So let us do the same drill for the other solution, pi, 0. Okay, so the other solution that I have, step 5, the other solution that I have is pi, 0. Now let us calculate A matrix there, the Jacobian matrix there. What is the Jacobian there? 0, 1, 0. These terms remain same, but this one becomes 1 now, right? Minus cos theta. Cos theta's value you figure out at pi. This results into 1. So 0, 1, 1, 0. Okay. Figuring out the value of Jacobian at pi, 0, I get it as 0, 1, 1, 0. What are the lambdas? Quickly see, just figure out the lambdas.
Plus minus
Plus
1.
minus 1.
Plus minus 1. Very good, very good. Plus minus 1. We are moving quite fast. Plus minus 1. Others are with us. Rest of the class, please tell us if you are here only. Fine. Okay. So lambda is equal to plus minus 1. So what is the conclusion? What is the conclusion? What kind of fixed point is this one?
Saddle.
Saddle, right? One side is positive, one side is negative. I have my stable and unstable manifolds lying there with the vectors, right? With the eigenvectors, if I figure out, I will have my stable and unstable manifold. This one is a saddle. Okay. Now let us draw the phase space once again. So we found the center. This is the center. Okay. And these were those small closed trajectories that we referred to, going on their own pace. Here, somewhere here, and somewhere here, right? Because whatever will happen at pi, 0 will be reflected at minus pi, 0. We are considering the entire angular axis here. And we understood that the same behavior will be repeated alternatively. Okay. So here and here, I see saddles. Okay. Can you quickly tell me what are the vectors associated with it? Then I can draw the lines and conclude that which one is the stable manifold and which one is the unstable manifold. So can someone tell me that what is vector 1, eigenvector 1 corresponding to say minus 1, and what is eigenvector 2 corresponding to plus 1?
For minus 1,
X is
for
equal to
plus
y
1
and x
it
is
is
equal to minus
1,
y.
1, 1, 1, and for
For minus 1, it is?
No, for
1,
plus 1 it is 1, 1.
Plus 1, it is 1, 1. Okay.
Yeah.
And what about the other
1
one?
minus 1. 1 minus 1.
1 minus
For
1. Very good. Let us
lambda is equal
draw.
to
So
minus 1.
please
Yeah.
try to draw. Okay. So this corresponds to lambda 1 equal to minus 1. This corresponds to lambda 2 is equal to plus 1. Very good. So draw those vectors here, the directions. Okay. 1 comma minus 1, that is with the negative sign, And that is my stable manifold, right? Because I have -1 associated here. How will that vector look like? 1, -1. How will that vector look like? On this spot, I will draw just the direction. On this spot, I will draw just the direction of the vector. So this is like that, isn't it? 1, -1 will be a vector that has this kind of a orientation, right? Similarly, 1, 1 is an increasing vector and that will have a direction like this. Okay? Just tell me if you have any doubt. Okay?
No.
Fine. Let us do the arrows. So first one, lambda1 is equal to -1 is going to be my stable manifold. Let us give the arrows towards the saddle point. 1, 1 is going to be my unstable manifold. So let us give the arrows away from the saddle point. Linearization. We will now extend these arrows beyond a certain proximity from the particular point. Just wait a minute. I am getting a call. হ্যাঁ মৃণাল দা ক্লাসে আছি হ্যাঁ 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 সেমিনারটা আছে ওই ছেলেরা দেবে 4 জন দেবে এই ক্লাসটার পরেই শুরু হবে আমি ওদেরই ক্লাস নিচ্ছি হ্যাঁ ঠিক আছে হ্যাঁ 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 ঠিক আছে হ্যালো yeah are you guys there okay so let us draw for this one as well. Okay, same vectors, same behavior, similar saddle here. So let us draw the 2 lines again. So here 1, -1 with arrows towards this saddle, 1, 1 with arrows away from the saddle. Okay, linearization is done. Now the last step to finish up the drawing. So some portions of the drawing is done. Now it's your intuition to extend this and see if it is working or not. So can you just extend these lines and complete the diagram on your own? How do you think the diagram will look like? Here I have an arrow which is going in and here I have an arrow going out. So if I connect these two like this and I connect these two like this, then the diagram becomes complete. Let us put some arrows here as well. Okay. So what about the trajectories in between? What about the trajectories in between? Here you had perfect circles, right? So in between you must have something like this, which is kind of an oval shaped, right? But still orbiting around the center that I had. Okay, this is kind of very similar to drawing those magnetic lines of forces. Okay, so you have some intuition from some point and then you just extend your idea about the system to get the entire phase space clearly. Okay, so is this part clear? Anyone has any doubt? What about trajectories beyond this particular saddle line that I have drawn, the manifolds that I, what do you expect? How will the lines beyond this will look like? Drawing the similarity from magnetic lines of forces, what do you think? How should they look like?
They will not enter the middle portion.
They will not enter, right? So they will just go on like this. Right? Put the arrows and this matches. At each and every point, you have to see that you are not deviating from the behavior that you see from the arrows nearby. So on the top, wavy lines like this, and the arrows, they will follow. You will see, they will just follow you as you go on. Okay? So the entire phase space up to a certain limit we have drawn, but now you can clearly get the idea that how to extend this further on the other fixed points. So the next center would be at 2 pi on this side. The next center would be on this side. On the other side, it will be on minus 2 pi. And the same thing you can just go on pasting side by side, right, to get the entire phase space of this system. Okay, drawing is fine, that whatever we drawn is fine. Now comes the physical interpretation. So push yourselves and try to understand that what is exactly happening at these stable and unstable manifolds. And these stable and unstable manifolds are really interesting because they are basically separating out the oscillatory behavior that we usually see in a pendulum with something else. What are these lines, these wavy lines that we have drawn outside? What do they signify, and what is signified by these lines that I have, the stable and unstable manifolds? And on top of it, these two are saddles. That means at some point, some direction, if you approach these points, they can also be like a stable point, right? So what are these points meaning? So this simply means, let me just one by one explain what each and every step means here. Okay, so this is the neutrally stable center, and for small energy values, if the energy of the system is small, okay, that is our older approximation, we have these nice and beautiful circles. Okay, so the pendulum was at rest, hanging straight down, and the lowest possible energy was there. Then you have some small energy applied, and the small oscillations start. Okay, traditional oscillations start. At a certain threshold value of the energy, which corresponds to these lines, the stable and unstable manifolds, you get the pendulum reach the inverted state. So the pendulum was like this, okay, and it reaches a state like this. The energy is so high, it reaches a state where it is completely inverted. Okay, it is like that. Okay, the saddle represents this point. The saddle represents this point as a saddle point, the inverted pendulum at rest. So as if it goes on like that and stops for a moment and then comes back and stops for a moment. So the other way, the completely inverted scenario is basically reflected by the saddles. Okay, so these trajectories basically, these trajectories that I have basically are telling you that it slows down to a halt precisely as it approaches the inverted position. Okay, it slows down at a halt to reach the inverted position before it reaches the inverted position. Beyond that energy, when the oscillation, the pendulum is just reaching the inverted part and coming back, if you put more energy to that, then what will happen? It will go on like this, right? It will go on like this. It will be erratically covering the entire over the top rotations, and these lines signify that. So that means you are continuously traversing more and more angles, right? You are not coming down back to zero. You are just going on traversing more and more angles. So you are covering the entire path. If your energy crosses that threshold, your angle crosses that threshold, then you are beyond that. So you go over the top and you start rotating like this. Okay, so this is the picture that we usually don't see, but this is something that we expect. So this does not deviate much from what we can expect if I push a system, a particular pendulum with a really high angle or really high energy, then that is what you expect, right? And here I just want to highlight one thing, that if you just go on drawing this several times on both sides, you see this repetitive behavior of the phase space. So this repetitive behavior is like this, right? So you see a repetitive behavior of the phase space where you go on seeing this repetitive circles and then saddles and the manifolds and so on, right? It goes on like that. So we call this particular behavior very much aligned to map it onto a cylindrical phase space. So a new term I am introducing here, cylindrical phase space. The phase portrait of this pendulum
Ma'am, your mic
वॉइस
is
चली
off.
गई क्या?
Hello, ma'am.
Hello?
Yes, your mic was off.
Hello?
Yeah.
Yes, ma'am. Yes, ma'am.
My mic was off the entire time.
No, no,
Not,
no, no.
not
Only for this few
only
seconds.
for
Only for a while? Only for a
Yeah,
while?
10,
yeah.
10, 15.
Okay, okay. So how far you have heard? The inverted part you have heard? Inverted pendulum? That is fine?
Yes, ma'am.
Yeah, another piece of paper you have
You
explained.
said the repetitive curve will be drawn, no? Right?
Repetitive
From
curve
there.
will come.
Yeah.
Okay, from there. Okay. So the repetitive curve will look something like this, right? So the repetitive curve, you have repetitively minus pi, 0, pi, 2 pi, 3 pi, and so on. This will go on like this. So this entire phase space makes much more sense if you wrap the entire thing around a cylinder. We call it a cylindrical phase space. So here I have a cylinder, okay, and I am trying to wrap this phase space around on this cylinder. So I start by a saddle here, okay, and I go on reaching the 0, and then when I reach the other side, if I just remove this part, and I stitch it on top of each other like this, okay, then I have this entire repetitive picture. Okay, you go on and consider that this is being repeated again and again, and there is no harm considering that. Okay, so this is the cylindrical phase space of phase portrait of pendulum. This is this entire idea of making it cylindrical makes sense because my v here is a real number, right, and theta is an angle. So the phase space not being on a flat piece of paper but being on a cylinder makes more sense, and that is what we see in case of pendulum. Okay, so the inverted pendulum at rest being at the two saddle positions, you can map it onto a cylinder, and we call it a cylindrical phase space due to the obvious symmetry of the system. Okay, so at this point I will stop and ask you to think about or just comment that the first question that Arijit has raised, that we said that it is kind of not good if I try to understand centers using these kind of Jacobian approach. Okay, so this particular system works fine, okay, but this entire idea can fail if you just introduce a damping term. So a small damping term, if you introduce into that, you cannot really understand this well using your Jacobian approach, just because it will not be captured anymore with the linearization only. So can you just simply but without doing that solution, if I just have this solution with us and just imagine that I have a damping in the picture now, can you just think that how this diagram will look like? Any crazy idea that how this diagram should look like if some damping is at the picture?
It will have spirals, closed spirals.
We'll
It
have
will
spirals,
eventually,
very good,
yeah,
which
yeah,
will eventually fall down onto the
fall
center,
down the
right?
center.
Yes. So what will happen to the stable and unstable manifolds? Try to draw that diagram. So just don't go for the equations. Try to solve that diagram by just simply extrapolating this particular scenario and your idea about damping. Fuse those together and try to draw this same diagram for a damped oscillator. Okay, I am sure you will be able to do that, or we will discuss that in the next class. Okay, so let us stop here. We have the seminar class now, so let us stop here for today. Okay, and we'll discuss about the entire energy related concept associated with this system in the next class, and finish up with pendulums in the next class. Okay, so let us stop.
Thank you, ma'am.
Questions? Any questions? We discussed it quite today, so I don't think there will be much questions. So